20 seconds and counting. T-minus 15 seconds. Guidance is internal. 12, 11, 10, 9. Ignition sequence start. Firing command coming in now. Ryan, you go for landing. Contact.
Roller coasters? Rockets? What have they got in common? Turn a chair upside down and you'd fall out. But on a roller coaster, you still keep your seat. It's all a question of motion. Forces make things move. But what's the force that brings us down to Earth? Watch this. Gravity. Nothing unusual about that. But what's happened? It takes about a second to fall 5 meters, but divide that second into 5. In each interval, the distance she falls increases. Use that to calculate the velocities and her velocity increases steadily, a constant acceleration of about 10 meters per second per second. But what does that tell you? Constant acceleration, constant force. So there's a constant force due to gravity. Given half a chance, it will accelerate us downwards. But usually, we aren't accelerated anywhere. We're standing on something. We don't feel gravity. We feel its effect on our mass, weight. Fair enough. But do you fall at the same rate if you're moving forwards? What do you think? Only one way to test it. He's running, she's stepping off. But if they leave the board at the same time, which one hits the water first? Surprised? What's up is going to come down. And at the same rate, too. Gravity. There's just no getting away from it. But maybe there is. Gravity always acts downwards. But what about this ride? Passengers at the top? Upside down. So why don't they fall out? Any ideas? Let's do some experiments. First, catch your volunteer. Convince him gently to take one of the cars on the ride. Look, no straps, but no falling bodies either. So what's keeping him in his seat? Experiment 2, same victim, but now with the help of his bathroom scales. Sitting on them before the ride starts, and he weighs 60 kilos. But will it stay that way? Certainly doesn't look like it. How can your weight change? First question, what's weight? It's a force, the product of an acceleration, gravity on a mass, u. Passengers getting off certainly don't look like they've gained any mass, more likely the opposite. and gravity is still the same. But if weight's a force, maybe the forces change as you go round the wheel. So let's measure them. Experiment 3. Take a mass of 2.5 kilos. Under gravity, that's a force of 25 newtons. Strap it into the car and on with the ride. Starts off hanging vertically, 25 newtons. Nothing unusual so far. But at the bottom of the ride, the force is greater, much greater, 75 newtons. So we've got an extra force coming from somewhere. How about at the top? 25 newtons, same as before. Or is it? No, the car's upside down, so it can't be due to gravity. This force is acting in the opposite direction, upwards. So what's going on? Right, let's take gravity first. Constant acceleration acts everywhere, always downwards. On this mass, a force of 25 newtons. But at the bottom of the ride, there's 75 newtons downwards. That's an extra 50 newtons from somewhere. Now for the tricky bit. Top of the wheel, gravity downwards. So what produces the 25 newtons acting upwards? Another force equal to gravity plus another 25 newtons. Again, 50 newtons. That's the force that keeps you in your seat. Always acting towards the outside of the circle. It doesn't feel constant because sometimes it's acting in the same direction as gravity, other times in the opposite direction. But where does the force come from? Seems that when you're going around in circles, interesting things happen. But let's take a simple example. A hammer thrower. When she turns, there's a force on the heavy ball of the hammer pushing it outwards, just like the wheel. Until she lets go. But as long as you've got hold of the hammer, there's an equal force acting inwards along the wire. Result, it moves in a circle. Letting go of the wire removes the force towards the centre. It flies off in a straight line. Same as the ride. There's a force acting outward on the passengers. Good thing too. And an equal force acting in the opposite direction. No wires this time, but the structure of the ride. Fortunately, no one's likely to let that go. But hang on a minute. Constant force when you're moving in a circle? Yes. But what do you expect from a constant force? Acceleration. But it doesn't look like the folk here are changing speed. Slow down the chairs and they hang vertical again. When there's a weight on a chain not hang straight, time to turn to the professionals. A pendulum in a stationary car. It hangs vertically. But what happens when the car starts to move? Let's take that one more time. Stationary car, vertical pendulum. But when the car accelerates forwards, the bob swings in the opposite direction and stays there as long as the car is accelerating. At a constant speed, the pendulum returns to the vertical. No acceleration, no force, just as if the car was stationary. And it doesn't matter how fast the car is going, as long as it's constant. Put on the brakes, the car decelerates. the pendulum swings forwards, again the opposite direction to the force. More force, bigger swing. So how about driving the car in a circle at a constant speed? What's the pendulum going to do? Camera on the door, and the bob's not swinging forwards or backwards, but it is moving. So let's try a different angle. Put the camera in the boot. Looking from behind, that pendulum is not vertical. It swings outwards and stays there. The car's moving at a constant speed, but the pendulum isn't vertical, so it must be accelerating in the opposite direction to the swing, towards the center of the circle. Higher speed, bigger swing, more acceleration. But although the speed is higher, it's still constant. Constant speed, but accelerating? How come? Well, what is acceleration? It's a change in velocity. Like when this roller coaster starts moving. But velocity and speed aren't the same. Velocity is speed in a particular direction. Here, it's in a straight line. But if you move in a circle, your direction is changing all the time. So your velocity is changing all the time, even if you're going at the same speed. Tricky, but it makes sense. It's easier to understand if we go back to the wheel. The wheel's going round at a constant speed. But take one car. First it's moving in this direction. Later on at the same speed, but in this direction. Then this direction. So the velocity changes even though the speed is constant. That's what's interesting about circular motion. And here's the ultimate in circular motion. Inside this contraption is a circular room. Inside the circular room is another victim. As the room starts to revolve, he's leaning against the wall. But watch what happens as the speed increases. Our man is pushed outward, as you'd expect. But spin the room fast enough, and the force increases. The wall doesn't seem like the wall anymore, more like the floor. A kind of artificial gravity. Faster spin, larger force. That might come in useful if you want to design one of these. But how can you be certain that your roller coaster is safe? It's all a question of velocity. You have to make sure it's going fast enough around the loops to stay on the rails. Screaming is fine, but falling bodies? Bad idea. But what determines how fast a roller coaster travels? That depends on how high you started from. And what provides the force? Yep, you've guessed it. Gravity. Riding a roller coaster or walking along, there's no escape from gravity. Or is there? We all know about spaceflight being weightless, but does that mean that when you're in orbit, you've actually escaped gravity? Certainly looks like it. That satellite must be about the size of a truck. Wouldn't give much for your chances of lifting that down on Earth. But hang on a minute. What about the moon? What keeps that circling the Earth rather than drifting off into space? It's certainly a lot further from the Earth than these astronauts. That force due to gravity again, which balances the force outward caused by the circular motion of the moon around the Earth. If the moon was further away, the force would be smaller, but gravity would still be there, like an invisible string tying the Earth and moon together. But the moon's 400,000 kilometers away. It hasn't escaped the Earth's gravitational pull. So how can these astronauts be weightless if the space shuttle was only 700 kilometers away? So it's not so simple. But where on Earth do you have no weight? Watch this. Did you see what happened to the force meter? Let's get him back on the diving board and try it again. Before stepping off, there's a force due to gravity on the metal weight. Nothing unusual about that. But watch the dial. Once it's falling, there's no force. The weight is weightless, and so is the person holding it. But how can a spaceship in orbit be falling? The whole point is that they don't, isn't it? Maybe there's no conflict. Think about launching a rocket. What would happen if the engines weren't very powerful? The force of the engines blasts it up, but the force of gravity pulls it back down. Try more powerful engines. It goes further, even further than you'd expect, because the Earth's surface is curved. But gravity still accelerates it downwards. Right, even more powerful engines. Gravity still pulls it back down, but the Earth is curved. It never hits the ground. The rocket's falling towards it due to gravity, but the Earth is curving away. Circular motion. It's in orbit. Astronauts? Satellites? Escape gravity? No. But weightless? Yup. Because they're falling. Continually falling towards the Earth, but never getting there. Fun, this weightlessness, but interesting too. For once you can see how things behave when they're released from gravity. Turning on the engines doesn't have quite the same effect as putting your foot down in a car. And taking exercise is pretty difficult. Maybe you can think of a solution. How could you give a spacecraft artificial gravity? So now it all makes sense. Things that move in a circle are accelerating, but not changing speed. Gravity brings everything down to Earth, except when it doesn't. A hammer goes up and comes down, but a satellite goes up and stays up, even though it's falling. It's as simple as that.